Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Welcome back to our course EMJ 44303 Power Electronics 2, and in this lecture we will learn about forward converter part 2, in which we will focus on the forward converter design. Okay, in this lecture we will learn about forward converter design, and it will cover the design step, the transformer design, output inductor design, output capacitor design, the switch design, and finally the diode design. Okay, for the forward converter design step, it can be a simple design or it can be advanced design. Okay, for both of them, first we have to know the requirement of the converter. For example, we can be given the range of voltage input, and then there will be a voltage output value, the switching frequency, output power, and some other value that can be given. For the simple design step, in which we will use for this course, for the transformer design, we just need to calculate the turn ratio. For the output inductor design, the inductance value. The capacitor design, we need to find the capacitance value. For MOSFET design, we need to calculate the voltage rating. And finally, for the diode design, we have to calculate the peak voltage. For more advanced design, in which you will face this during your working life in industry, let's say for the transformer design, you have to calculate the turn ratio, the core size, minimum number of turn to avoid saturation, the wire size, the structure of the winding, power losses, and thermal capability. So these are the considerations that you might have to deal with during the transformer design. For the output inductor design, other than inductance values, you have to calculate the losses. For the output capacitor design, there will be a voltage rating, RMS current rating, and some transient consideration that you must take during the output capacitor design. And as well for MOSFET design, you need to consider the current rating, switching frequency, the switching frequency rating of the MOSFET, snubber circuit, and etc. Okay, for the diode design, other than peak voltage, we need to calculate the average current, the peak current, and any voltage drop, okay, in the diode. Okay, this figure shows the forward converter, and I mentioned before, the one that we need to design is a simple design. So basically, usually we will be given a voltage range. Okay, let's say from 130 volt till 200 volt for the input, and then for the output voltage, usually we will be given only one value, and then you can be given other parameters such as output current and then the frequency. Okay, if the frequency is not given, maybe it asks us to define itself what is the switching frequency that we want to use. Okay, so for the design, we need to determine, okay, for the transformer, we need to determine the NP over NS over NR. So you need to determine the turn ratio of the primary, secondary, and reside winding. And then for the switch, we need to determine the voltage rating. For the diode rating, okay, we have 3 diodes. We need to find the voltage rating for the diode, and then we need to determine the inductance value as well as capacitance value. Okay, this is the first step of our design, to design the transformer. Okay, for the simple design, we just need to find the turn ratio of the primary, secondary, as well as the reset winding. Okay, this is the output voltage equation for the forward converter, in which the output voltage is equal to the duty cycle multiplied by the NS over NP, secondary winding over primary winding, multiplied by the input voltage. Okay, to achieve the required output voltage, the turn ratio must be calculated using the minimum magnitude of input supply and maximum allowable duty cycle. Okay, so to find the best possible configuration, we have to use the minimum magnitude of input supply and maximum allowable duty cycle. Okay, so for the reason why we need to use this, so I give the responsibility for student to find the answer for this. Okay, so when we arrange the equation here, we have the ns over np equals to v out over d max multiplied by vi min. To consider the effect of leakage, inductance, winding, switch resistance, device draw, and transition requirement, usually we will have a factor added into our equation to take care of all of these parameters. Okay, leakage inductance will cause the voltage drop in the output voltage, and as well as the winding and switch resistance. So to cater for all of this, we will take a value of km. So this is a margin factor between 0.9 to 0.95. So if you use this range of value, it should be safe enough. So where do you put the km? You have to put at this, okay, at the input side here, vi min, so multiply by the margin factor. Okay, now we come to the second design criteria, which is the inductor design. So theoretically, there is no upper limit for the inductor value, okay, because if we can use the biggest inductance value, our circuit should be working fine. But the problem of having a big inductance is much heavier, okay, and it will increase the losses. So usually we will find the sweet spot and find the optimum value of inductance to make sure that our circuit work as required. Okay, the DC value of inductor current is equal to the load current. What you mean is, let's say our rated current is this one, so our inductor current will flow usually like this. Okay, for the CCM, it will flow like this. Okay, the output inductor must have an inductance value large enough to ensure the CCM at 10% of the design load. So this is usually the requirement. Okay, it will be given in the question. Sometimes the question will ask, we have to make sure that during the 10% of the design load, our circuit is still operating in CCM mode. So what you mean by this 10% is, let's say, okay, we have this I rated, let's say we have 10 ampere, okay, just give it a value 10 ampere at this point. So we have to make sure if our load is very small and our current will go down, even at the 10% of the rated current, so let's say this one is 1 amp, during at this time as well, our circuit is still operating in CCM. So we must make sure that our inductor current flow like this. Okay, so the delta IL will be from here to here. Okay, and then this is the ILDC minimum, the one that we have to define or design in our inductor design. Okay, so this is with equation. So we have the ILDC min equals to 0.1 multiplied by I rated, I out rated. So I out rated is this one, the green one. And then we have here the delta IL from the minimum here until here. We have 0.2 multiplied by I rated, because this is 0.1. So if you have the peak here, this one is 0 and this one will be 0.2 I rated. Okay, for the IL min, this is equal to ILDC min minus delta IL over 2, and this one, it can become 0. Okay, we have to make sure it is 0 or bigger than that lah. We cannot have value of negative here. Okay, so that's all the equation we have in for this inductor. Okay, now we have the equation for delta IL. Okay, delta IL is equal to the T on, the time during the converter switch on, multiplied by ns over np multiplied by vi minus vout divided by L. Okay, we know that for the duty cycle, okay, the duty cycle is equal to the on time multiplied by the switching frequency, and then we will substitute this one into the output voltage equation. Okay, we have here. Okay, so the D equals to T on Fs, okay, multiplied by Ns over Np. So for this calculation, okay, we don't have to include the margin factor. Okay, remember the margin factor we input during the design of the transformer. So for the inductor design, we don't have to input it. And then we find the value of T on. We need to define the value of T on. T on is equal to V out over Vi divided by F multiplied by Np over Ns. So this is the on time. Okay, so finally for the L min, okay, L min, we will replace the T on, okay, with this value that we just got before this, okay, multiplied by Ns over Np Vi minus Vout divided by delta IL. Remember the original equation is delta IL is at this side divided by L. So we want to find the L, so L is moved to this side, delta IL is moved to this side. Okay, and then we know from our diagram before this, the delta IL is equal to 0.2 multiplied by IO rated. Okay, and then if we substitute all the value here, okay, and finally okay, remember for the Vi here, we must use, okay, to get the highest value of L, we must ensure that we use the maximum value of Vi, okay, because this is 1 minus sometime if we sum value here. So if we use this one is big value, okay, so we can get the maximum value for the L. Okay, and then when you manage to find the value of inductor, so for the design process, usually we will use the standard inductor value. Okay, we cannot just simply use, let's say 1.23 okay, 1.23 microhenry. So we must use 1.3 microhenry, the one nearest to our value, or the biggest bigger than our value. Let's say the calculation get 4.35, so we cannot use 4.3, so we must use 4.7 microhenry. So this value will be given, okay, if the question come out in your final exam, this standard value will be given. Okay, next we are going to design the value for capacitor. So the capacitor design must be chosen to meet the output voltage ripple specification. So usually when we want to ask student to find the value for capacitor, so the most important thing to be given is the output voltage ripple value. Okay, this is the IC waveform. Okay, so the delta V out, okay, this is the delta V out is equal to the delta Q, okay, the area in this waveform, okay, the positive side, okay, divided by C, okay, this is the capacitance value. So the delta Q, the equation is half multiplied by delta IL divided by 2. The delta IL divided by 2 is the peak value here, and then we have Ts over 2, okay, the duration from this to this, okay, this is Ts over 2. So overall you will get the capacitance equation is delta IL divided by delta V out divided by 8Fs. Okay, and then if we are required to find the IRMS, this is the equation for IC RMS. Okay, the same with the inductor design. So for the capacitor design, we also have to use the standard value, and this one will be given. So if we get some value and the value that we get is not a standard one, we have to use one size bigger than the one that we designed. Okay, the next one is the switch design. Okay, why we need to determine the voltage rating of the switch? Because during the switch turn off, our switch will face or have to withstand the big value of voltage during the switch turn off. Okay, so the equation is the V switch is equal to V input plus the V peak, the V primary, sorry, okay, the V input plus the V primary. This is during the switch turn off, and the equation is VI max multiplied by 1 plus NP over NR. So this is the maximum voltage that can be seen by the our switch here during the switch turn off. And then finally, we are going to look at the diode voltage rating. So the peak voltage for the diode 1 is NS over NR multiplied by VI max. The same goes for the diode 2 because they are located at the same side, the output side. For the D3, the peak voltage is equal to NR divided by NP multiplied by VI max. Okay. Okay, now we come to the example for the design of forward converter. These are the parameters given to us, and this is the value of the parameter. The first one is the input voltage. Like I mentioned before, usually this will be given in a range of voltage. So in this example is from 130 volt until 200 volt. So what it means is we have to make sure that our converter is operating normally within the required value. When we receive the lowest input voltage 130 or when we receive the highest input voltage 200. So within this range, our forward converter must work as required. Then we have the output voltage equals to 3.3 volt, the maximum output current, so this is the rated current 20 ampere, the maximum power 66 watt, the switching frequency is given, in this case 100 kilohertz, and for the output voltage ripple it is 0.4%. So we are required to design the forward converter including the transformer, inductor, capacitor, switch and diode. Consider a proper margin factor for the transformer design. So this is the requirement for our design. For the first step, okay, we go for the transformer design. Usually to make the design easier, we can assume that the reset winding and the primary winding are the same. So by having the reset winding and the primary winding the same, so we can have the maximum duty cycle equals to Dmax equals to 1 divided by 1 plus NR over NP. So when NR and NP is the same, so the value will be 1 divided by 2. 1 plus 1, so 1 divided by 2 is 0.5. So there is sometimes the question can ask you, so we want to make sure that the maximum duty cycle is, let's say, more than 0.5, let's say 0.6. So we have to make sure that we have a proper ratio for NR over NP. So to get 0.6, you have to calculate what is the required value for NR and over NP, so that we can get the value of 0.6 for the maximum duty cycle. For the winding ratio for the primary and the secondary winding, remember we can use this equation and to add a margin factor 0.9 because we want to consider the effect of leakage inductance, winding, switch resistance, etc. So we can use this equation and we substitute everything. Remember, this is the minimum value of the uh, input voltage, and we have to use the maximum value for the duty cycle. So when we calculate this, we will get Ns over Np equals to 0.0564. Okay, if we inverse that, Np over Ns, okay, we have 1 over 0.0564. We get the ratio of 17.7. Okay, so our ratio, our rating or our winding ratio must be less than 17.7. So in this case, the nearest value we can select is 16 or okay, 17 is also okay, but let's say we select 16 in this case. So our ratio will be Np over Ns over Nr equals to 16 over 1 over 16, because our Nr is the same with Np. Okay, now we move to the inductor design. The output inductor must have inductance value large enough to ensure the CCM at 10% of the design load. So usually if it is not mentioned, we can play safe by having the assumption that this is required for the converter to operate at CCM at 10% of the design load. Okay, we already have the minimum inductor value equation, so equals to V out over 0.2 multiplied by IO rated multiplied by switching frequency multiplied by 1 minus Np over S multiplied by V out over Vi. So when we substitute everything in this equation, okay, so this is the minimum value, so we have to make sure that our inductor is bigger than this minimum value. So when we calculate this, our minimum value is 6.07 microhenry. Okay, so when we look at the table for the standard value of inductor, the nearest value to this one is 6.2 microhenry. We have to select the one bigger than this value, so it is 6.2 microhenry. And now we move to the capacitor design. So it is required that output voltage ripple must not exceed 0.4%. Okay, so what it means by the 0.4% is the delta V out, okay, divided by V out is equal to 0.4%. So the 0.4% is 0.004 multiplied by V out. Okay, we want to find the delta V out. Okay, and then the value is 0.0132. So this is the value for delta V out. So why we need to find this? Because we want to plug it into this equation. So the capacitor value is equal to the delta IL divided by delta V out, okay, and then multiplied by 1 over 8 Fs. Okay, when we substitute everything in this equation, we will find the capacitor value is 0.000378, or in other term we can call it 378 microfarad. 378 microfarad. Okay, so this is not a standard value, so we must find what is the standard value for the capacitor. So the nearest one is 470 microfarad. Okay, so we can verify that using this value, our delta V out over V out here, okay, if we use this value, our delta V out will become 0.0106. okay, if we substitute everything here. Okay, we substitute C into this equation, we will find our value of delta V out is 0.0106. So if we want to find the voltage ripple, okay, delta V out divided by V out equals to 0.0032. So this is 0.32%. okay, which is within our requirement of 0.4%. Next one, we have to consider the switch rating for the V switch. Okay, when we plug in the value here, because this one is the same, so our V switch will withstand the voltage double of our input voltage, which is 400 volt. Okay, so when we want to select the switch for the voltage rating for our switch, we have to find the value more than 400 volt. And finally, for the diode, the voltage for the diode, okay, the peak voltage for the D1 is Ns over Nr multiplied by Vi max, so it is equal to 12.5. The same is the diode 2, 12.5. And for the diode 3 is Nr over Np multiplied by Vi max, so you will get 200 volt for the D3. Okay, so that's all for the inverter design lecture and example. So I plan to make a group of students to come up with their own design, and you have to discuss and finalize your design and submit the video to me. Okay, the instruction will be given in the Google Classroom. So with that, I thank you for your attention and see you in next class. Assalamualaikum warahmatullahi wabarakatuh.